Hello, good morning, pre-calc. We're looking at limits again today, and our learning target stays unchanged. You'll be able to use limit notation to find the left-hand limits, right-hand limits, and two-sided limits. And you remember that we've described a limit or defined a limit as the y value, the height, the function value that a function approaches as the input approaches some x value. So we've got the word approaches shows up both describing what the height is approaching and what the x coordinate is approaching. And so I've given us an analogy to help understand that. We use Dread Pirates. So we got these two pirates, the Dread Pirate Leslie at the left side of the graph and the Dread Pirate Roberts coming from the right side of the graph. And they sail as close as they feel like getting to some point. It's arbitrarily close or arbitrarily close, which actually is a math word. It means, we get as close as we feel like getting. Arbitrarily means we decide, or it's been decided without really, a specific definition of this is how close you have to be. It's like, hey, you get as close as you can get. Maybe you get all the way there. Maybe you just get pretty close. Maybe like, oh my gosh, the wave is too big. I don't want to get closer. Or maybe you can actually sail up right on top of the wave. It just depends on the pirate. So we want to look today at some more challenging graphs. We got some more going on here. So let's focus our attention here. So I've got a whole set of questions related to this one graph. Let's look at one kind of bank of questions at a time. So first, we got a set of limits here all around the x coordinate of 0. So I've got a right-hand limit. It's got that little plus sign there. X approaches 0. We've got a left-hand limit. As x approaches 0, we see the little minus sign telling us it's the left-hand limit. The two-sided limit, x approaches 0 again, does not have a little plus or minus in the spot where the exponent would be. There's no superscript at all. And so that tells us it's a two-sided limit. And then lastly, we've got a function value also at 0. So there's a whole bunch of stuff going on in the graph. It is discontinuous. It's got pieces all over the place scattered across the graph. And we do not need to pay attention to any of it. So this first set of questions all focuses in on what is happening at an x coordinate of 0. So this piece of the graph, we don't need to pay attention to. This piece of the graph, we don't need to pay attention to. Not right now. So Leslie sails. None of this stuff matters. All that matters is what's happening right here. As he is approaching as close as possible to an x value of 0, what height is he heading for? It looks like as he sails down this little downslope, it looks like he's heading right for a height of 4. I'm sorry, I started a little bit out of order. I grabbed my left-hand pirate, so we're going to go with the green box right here. That left-hand limit of 4. And so you can think of reaching your left hand out, grabbing onto that graph, wrapping your fingers around it, and as you slide down the graph, where's your thumb headed for? That is a left-hand limit. And so you'd be heading right there for 4. All right, let's get the boat out of the way and leave the graph alone. So the right-hand limit, sorry, this is out of order again, but let's do the blue one. So the right-hand limit, there's nothing over here that doesn't make any difference. Some people overthink my analogy, and you're like, but the Dread Pirate Roberts is supposed to start at the right end of the world at Port Plus, and there's no graph to sail on. How does he get from Port Plus to the graph? That is a fabulous question, and you've exceeded the bounds of my analogy. All right, magic. Right, that's the explanation. So, because that's the way the story works, maybe that's a better explanation. Bam! Dread Pirate Roberts appears on the graph and is sailing towards an x coordinate of 0. So just this little chunk of graph right here is all we need to pay attention to. And as Dread Pirate Roberts sails down this little curvy thing, seems like his boat is destined to arrive at a height of 4. We know that he doesn't actually get there. He can't get there. Neither of the Dread Pirates can actually get to an x coordinate of 0 and a height of 4 because it's an open circle on the graph. It doesn't exist. It's there for visual reference. That is not the spot where the graph exists. We'll get to that in a minute. That's our function value at the end. Next, we have a two-sided limit, and in our little notation above the zero, there is not a superscript. It's not a plus, there's not a minus. So that tells us it's a two-sided limit. Two-sided limits mean, would both of these two pirate ships sail towards the same height? They would. We know that because our previous answers are the same. Or, asked a different way, if you grab on to both parts of the graph and you're heading towards zero, your hands meet. Is the graph connected? Do your thumbs point to the same place? All of the above. Yes. All of that happens. It's 4. All right, we got the same answer for the left and right hand limit. That'd be one way of thinking about it. If we look at the graph, we can see that the two branches of the graph do connect there on the graph. They're drawn together. It's an open circle, but the two parts of the graph touch. So a two-sided limit does exist, and it is that height 4. The function value, we need our little graph walker. And our little graph walker, if he tries to stand on that open circle, he does not have the same outcome that the pirate ships have. He falls through the hole because it doesn't exist, and oh my gosh, falls down there and lands on the closed circle. This is what graph walkers do. They walk on the graph. If there's an open circle, that doesn't count as graph. They can't stand there. They can't walk there. They magically go to where the graph exists, on that closed circle. So at an x coordinate of 0, the function value is -3. That is the height where the graph actually exists in the form of a closed dot or line, right? Well, in this case, it's a closed dot, but it doesn't have to be a dot. Function value would refer just as well to the curve or the line if it exists at that point. Okay, so we have some more questions over here, same graph. This second set of questions refers to what's happening at the graph at -5. So I got a right-hand limit, we see the little plus. I got a left-hand limit, we got the little minus. The two-sided limit, it is a negative number, but the superscript does not have a plus or minus, so that tells us it's a two-sided limit. And lastly, the function value, all of these at -5. So I'll move everything into position. All right, so let's start at the top of the questions this time. The right-hand limit with our little plus sign as the superscript. So the Dread Pirate Roberts, ignore all of this part of the graph. It doesn't matter for our question right now. We just want the piece of the graph that Roberts is sailing on as he approaches -5. And it sure looks like he is heading for this height of -1. So -1 for the right-hand limit. In green, the little minus sign tells us the left-hand limit. So Dread Pirate Leslie sailing along this chunk of graph that will lead him towards an x coordinate of -5. And it sure looks like he's sailing right for that height of 8. Then the two-sided limit. Did those two Dread Pirates both find the same height? No, they did not. If you just looked at the graph, do the two parts of the graph connect to each other at -5? No, they're totally disconnected. It's a discontinuity. The two pieces of the graph are not connected to each other at that x value of -5, which means the two-sided limit does not exist. And lastly, the function value. I've got my graph walker already into position. So at -5, what height is the graph walker going to be standing at? Find the closed circle. Or in other cases, it may actually be just a line, wherever the graph, what height is it at on the line there? Well, this time it's at 8. All right. All right, well, we're on the same graph. Let's look at one more thing. We're going to look at what's going on at 2. +2. So I got right-hand limit, 2 is positive, but then the subscript plus tells me there's a right-hand limit in green. The little minus sign in the superscript spot there tells me it's a left-hand limit. The two-sided limit has no superscript, and then I got the function value. So let's start at the right-hand limit up there at the top. So as the Dread Pirate Roberts sails out of nothingness towards an x coordinate of 2, what height is the Dread Pirate Roberts approaching? Well, what is Dread Pirate Roberts actually sailing on? There is no graph over here. So we could sit right on the x value of 2, but there is no way for the Dread Pirate Roberts to approach 2. It just would be at 2, right? And that's not what limit notation is about. It's not like where are you when you're at 2. It's what are you sailing towards? What are you approaching? Roberts has nothing to approach on. There is no right side of the graph, right? In this case, it actually is probably better for us to, that didn't work, did it? To lose our pirate ship. And just think about grabbing onto that graph with your right hand. So here's where 2 is, where my mouse cursor. And so you're going to take your right hand, you're going to try to grab onto the part of the graph that's on the right side of that. And there's nothing to grab onto. You can't do a right hand limit because there is no right hand side of the graph there. So does not exist. You can have right and left hand limits that do not exist. We've seen two-sided limits that do not exist. You can have right hand limits that do not exist. You can have function values that do not exist. If I ask you what's the function value at like 6, there's no graph there. It doesn't exist. Right? Okay, well, I'm not asking you that. Let's stick with what's on the page. So left hand limit as x approaches 2 from the left. So all of this part of the graph right here, none of that stuff makes any difference. All I care about is this last little piece of the graph that Leslie would be sailing on as he approaches x value of 2. And on this last little bit of the graph, curving towards that height right there, 6. Right, so my left-hand limit is 6. Two-sided limit, you can't have a two-sided limit when there's only one side. Right? We already talked about the right-hand limit doesn't exist. Well, neither does the two-sided limit. There's not two sides. I can grab on with my left hand, but my right hand, I just keep missing. There's nothing to grab onto. Can't have a two-sided limit. I can't get two hands on that graph. This one does not exist. The other way you would explain it for the two-sided limit is that the two parts of the graph, do they attach and touch each other at an x value of 2? No, because there's only one part of the graph. All right. Excuse me, Dread Pirate Leslie. I need to have some space for my graph walker. Function value. This is more straightforward. Put the graph walker on there. Where do they stand? They stand at a height of 6. All right. So we can see some funny stuff going on with graphs. Don't overthink it. If there's not a right-hand side, or in a different case, if there was not a left-hand side, then does not exist. And graphs don't have to all be attached. We don't have to overthink about, like, what about all that other stuff over there? How does the pirate even get from here to there? It's like, that doesn't matter. All we're looking at is what's happening right at the x value that the notation tells us to look at. Nothing else has anything to do with what we are looking at.